right? Okay, never mind. The scripts are here. So just for you, how many of you have not collected your exam, the midterm exam? So see the names today, right? Okay, very good. So for the midterm exams, if there are any concerns about the grading, you can see me to adjust. Okay, there are probably some minor errors in there, but the reason why this happens is because I was rushing through it, and I'm returning all your scripts to you, so I know if there's an issue, you'll find, correct. So I'm not concerned. In any case, not to worry about the final exam. Final exam, first the scripts are checked by another prof. Second thing is that what really happens is that I will mark everything, okay? And then I will put out the scores, look at the scores, and those fellows who are, smack in the middle of like A's, I don't really care, hardly matters. Then those people at the borderline will look at all the scripts carefully to see whether you deserve more or deserve less, okay? And then go and figure out what kind of a score you deserve. So, to be honest, don't worry too much about the grades, because what's going to happen in this class is that you will get a grade that is commensurate with your ability, okay? Now, you need an A minus or higher to do 2020. Those who have B plus can appeal to do that, okay? So last year we had a few students who had B pluses and appealed to do 2020. Sadly, they didn't do very well, okay? Because the fact is that the A minus and B plus, there is a gap, okay? And the way that I decide is I look at the past years, all the students, I've taught the class many years, so the standard turns out is preserved across years, right? And if you get a B plus, it probably means that you are not quite, you need to practice more, and 202 may not be the most appropriate pace, okay? Because last year, the Seth, who was the guy who was teaching 202, he was, he said, okay, fine, B plus, if you want to appeal, let him do. But it turns out that statistically, we look back and we see that the people who actually got B plus in 11S and who didn't do very well, okay? So the point here is not, okay, let's look at this. The point here is not to try to getting a better grade may not be a good thing if it's not the correct, the appropriate grade. Okay. And for most of you who didn't do quite so well, not to worry, because this happens. Most of you, this is the first exam that you're taking at NUS. This is the first exam of this sort that you're taking at NUS. Life in the world is different. We'll give you a chance to redeem yourself next week, and you have a chance to redeem yourself in a PE again. Okay. Last year, statistically, 70% of the class get A's. This year, I don't think it might be more. Okay. I would think that, and if you look at A's, then probably it's because your level of efficiency isn't quite the A level, and you should just work harder. Okay. I don't get paid more if you get more A's. I don't get paid less either, so hardly matters to me. Okay. So any concerns or questions for our midterm exam? Okay, never mind. Let's quickly address all the issues. Now, so first of all, thank you for completing the survey. We have, surprise, 100% response rate. It's so delicious. And I don't know, since last year for some strange reason, we always have 100% response rates. And quite fun too, very amazing. So anyway, I issue orders for Zuhan to basically go and issue everyone I do this achievement. This achievement is not forgiveness, used for people who want to have this broken streak thing. Basically, the whole point now is that if you have, perfect, and then one thing, blew up, very perfect, you can kind of erase one of these things to complete your streak. Okay, this is used manually in the filter at some point. Okay, so essentially what this does is that it exchanges this achievement for the so-called higher level, which is the perfect streak. Okay, anyway, it's random. Okay, next, so today I'm pleased to announce the contest winners. Okay, pause attention. Okay, first four crystals. Okay, four crystals. It turns out the following the finalists that are. Wow. Okay. Okay, this is how it looks. How come? Okay, never mind. So this is the list of finalists. Then again, you just affect them. Okay, so I think the average score here for midterm is like 90 something. Okay, so maybe contests are good for you, right? The more people you contest, the better your score will be midterm. It's true, right? I mean, that's good, you said, right? Okay, the reason why is that on like something right on average. Okay, so among them, honorable mention goes to the gentleman Aldrich, who is not here today. Okay. Who's the participant? Who wants to try the back and give him? Okay, fine. There you are. Congratulations. Okay. It turns out there are two winners, okay, for this contest, because one is what you call the fastest. Okay. And now, yeah, you got right. Okay. Thank you very much. Okay. And the guy with the best solution, or the shortest number of times, is Mr. Chan. Thank you very much for the participation. Okay, so today is the collectible yellow color badge. Okay, and very good. Next one. Okay, so the high kick problem. Okay, high kick problem. Apparently, a lot of people do the kind of thing very naive. So the only two finalists for this one who actually went to do much better than the average. Okay, and finalists are Mr. Chan again. Okay, and Mr. Yang. Okay, so the two of them basically are the two who, get on that, huh? Yeah. Not really, I think it's very wrong, right? So anyway, it turns out that the winner is Mr. Yang. Okay, so Mr. Chan, effectively, you're going to do that, just get one back, one question. Okay, thank you very much. Okay. Alright, so after this, okay, I'm going to see this thing before I announce you the XT. After this, again, this afternoon, all the XT will be awarded to the winners. So how many XT you get depends on whether you win or not and how well you do. Very good, huh? Okay, now let me quickly, okay, I know this the business survey we put online. I'm not sure how many of you read it, but let me quickly highlight some of the key things. First of all, thanks a lot for responding. It's really good to have 100% response rate, better than the normal teaching feedback. So I guess the achievements are more useful than winning points, right? Okay, so anyway, background, who has background? About 70% of the class has background programming. Okay, now, so it turns out that last year also 70% of the class have programming background, and although about 70% of the students got A's, they are not correlated, not completely the same. So which means that programming background doesn't always help. Okay? Because the truth is that you have learned something, but this class is not about programming, you know C++, whatever, doesn't matter. The question is how fast can you solve the problem on the spot. Right? So this class is not about stuff you know, or whether you know how to do C++ or C. It's about whether you can solve problems. Okay? So in fact, some of the people who have no background have done quite well in this exam. Okay? And some people with background didn't do well. Okay? So the point is this is random. Okay? This was last year. Okay? Now teaching since the lectures are good. Okay, I don't think I've actually improved that much in lecturing. I really don't think so. Because 6 years, after the last 5 years is the same. So I think what really happens is that this year, the paths are really useful. Okay, I'll talk about later. Repetition and DG will drop a bit. The main reason I suspect is class size. Okay, last year DG was 4:1. Because I had 30 people. So usually I had 4 students, no wrong, not 4 students. 4 students, 1 tutor. Okay, so obviously last year I think they had a lot more personalized attention. The repetition also quite nasty. This year the first repetition is really huge. The biggest I've done in my life. Okay, so obviously the quality of teaching has something to do with the student-teacher ratio. This is a lot. So but I think not significant. I think overall it's a good teacher. Okay, so apparently nobody compared I speak too fast compared to like X numbers a year. So this is amazing. Okay, interesting. So last year, okay, I don't publish all the posts, all the user feedback, but last year's most common adjective was brilliant. This year is not so brilliant, but this year's most common adjective is helpful. So almost every tutor is called helpful, so that's kind of nice. I personally think that helpful tutors are much better than brilliant tutors. To be honest, okay. So last year, they say every year is quite brilliant, but this year the key adjective is helpful, so I'm quite happy about this. and this is the thing that I think really matters. So basically, you think that my lectures are better, but I suspect the reason why this happens is because of the past. Now, the past is a very evil invention, invented by Zuhan, okay? And it causes a lot of grief, that's a lot of work to basically put in data. Alright, now the point of the past, okay, somebody complained that the deadline is too short, right? Okay, but this is intentional. Why? Because the problem with students is that they go away from lecture thinking that it's clear, but actually it's not. Alright. Now, then the problem with the class is that obviously one lecture goes for the last lecture or the two previous lectures. Then many students go thinking they're clear but they're blurred. Okay, then they don't actually go and figure it out, okay, before the next lecture. So when they come, they're still blurred. So this makes life kind of worse, right? So what we do is for this past thing, we have this deadline thing, so we simply force all the students to get on top of the material before the next lecture next week. So I think this actually helps improve the clarity of the lecture, right? And the past system is kind of cool because it's really quite, we cannot see it, but we can see every single thing you all do, we can see. Students, okay. So one of the problems one of the problems you have in midterm is that sometimes you get this wrong. But then in the missions you can do. Why? Because now you are doing this thing called programming by anyhow whacking. Okay? This will work to some extent for the practical exam because you have the doctor record. Okay? But at the end of the day, we want to discourage this behavior because it wastes our time. Okay, you waste our time. And it's not training the kind of thinking that we want to train. Okay, so hopefully, the past system allows us to see who's doing anyhow whacking, and some people are doing it. Okay, and also when you get stuck, we know, and the teachers will come in. I will check once in a while who's getting stuck, who has not done the past, who's getting stuck, and we know where you get stuck. So this is really helpful. I think this is where we actually did well. Okay, time spent. People are actually spending less time on the assignment this year, but this is actually intentional. We have actually scaled back. Okay, some have been reduced, some assignments have been removed. Something that's simpler. Fundamentally, because last year when we first rolled out the system, this is the story there. Cycles are really meant to be optional. But somehow everybody it's actually very clever. I mean, this year is different than last year. Last year I think like 80% will do the cycle. This year I think everybody doing cycles. So the truth is that, and to be honest, it's not very funny, but we don't kill ourselves last year because the grading also was terrible. Because especially the cycles is actually to help people make up lost EXP. But in the end, everyone doing it. But everyone doing it, then the teachers grade are crazy. Okay, so we work for everybody. That's why it's a bit less than last year. And it's also reflected in this thing about only 5% thing that the missions are killing them. Last year, 15% started killing them. So either you're smarter or we'll do better. Okay, and one person say another word forward, please. Every year, no guy like that. Okay. Midterms seems harder last year, but then 5 people, 5 say it's too easy. And then I think the main problem is not that it's harder, right? The main problem is really the time, okay? But exams are hard to set, But on the whole, I think the class did accept pretty much. I aim for a certain number with 70. Okay, you got a little bit lower than 70, but it's fine. Right, because fundamentally the whole point here is the people who know what they're doing, obviously it's clear in the exam. Those who kind of know what they're doing, the people who have reasonable mastery, the A's are there. The people who are a little bit, who either are a bit slow in solving problems or who are not completely clear, we also can see. Because you don't need help, we can also see. Okay, so to some extent, this midterm is more diagnostic than it is assessment. I mean, it's more diagnostic than assessment because fundamentally we are not here to try to assess it at this point. What really matters to me is where you end up at the end of the class. Clearly you don't get smarter all the way, right? Okay. So I guess I will have achieved my job if you all get smart at the end of the class. Okay. Now not that smart, then it's okay. Okay. As long as at the end of the class you get smart enough, that's good enough. Okay. So the weighting is just that this is 15%, which hardly matters. Okay. And then PE is very important. The two key things are PE and final exam. Why? Because PE ultimately is whether you can actually do the stuff. Okay. If you can actually solve problems, then you should be okay. So the PE will have probably, I haven't said yet, okay, we'll have 4 questions. First 2 questions is kind of standard. That means the good students, A+ students should be able to solve the first 3 questions which are within 45 minutes. Okay. Although it's not 45 minutes. Okay, because the level is around 43 questions, definitely you get A already, because that shows that you have sufficient mastery. The last question is for 5 took out all the time. Okay. And that one is basically to decide on the A classes, and for those people who demonstrate that you actually figure out that means you actually prove okay, to kind of get back some points. So the excess points from the PE will go to the midterm. Okay, game midterm 60% like this. This is the same as last year apparently. So apparently 60% gamers, 30% not gamers is very fine. And then 45% think data are helpful. 30% stresses them out. Again, these numbers are very common. Last year, those similar numbers. I guess the people in the middle don't really care. Okay, but okay, this thing that we do about is that there's less mobility. This will reduce social mobility, and the reason is very simple because okay, see last year I thought was that you only get extra after the teachers grade the assignments. Okay. But then they are unhappy saying that basically you want to get extra points right after you submit, right? Then you get this, you want to get some fictitious EXP, right, which confirms after the grade, right? That is the new version. But the problem with this system, the last system with the actually causes churn, right? Because the tutors, one thing this is also not so fast last year. Last year the tutors were a bit slower. This year the tutors were on, they are like great within I think Patrick is a few hours finish grading already, on average. So last year the tutors can spread between 1 up to 1 day. So the tutors having variation actually causes some churn in the report. That was kind of interesting. Okay, this year left with the word churn. Okay, and this year 97% think the class is cool. 1% think the class is not so cool. I think we can figure out who it is, but it's okay. We'll try to help her. Okay, now next thing is that the work thing, too much work. Okay, so the point that maybe some people think that the class is much work, right? But then the thing here is that there are people who ask for more practice. Okay, just quickly, let me just address this. The more practice thing, part of your exam script here. Okay, for this practice, essentially I think we have a lot of practice here. Right, there is an exam review, for the practice exam review, there's a W task list, okay, we have the pass, we have the VGs, got the missions, a lot of stuff, the factors and the concepts. Still not enough, this is the solution. Go to SITP, you can do this question at SITP. SITP finish really, still not enough, there are two supplementary books, right? There's this thing called How to Design Programs, and also this one called Concrete Abstraction. Okay, so let's go and look at those books and do. Still not enough, right? There's all the master exams, plenty of them, okay? So who finished every master exam or midterm? Who finished trying all the past midterm exams? Only one. Hey, don't be shy, I love you. The only one that I love you, can you please, follow this gentleman and harder. Okay, so whoever you put down this thing, more practice, can you please make sure you finish all the past exams for practice? Okay? Now, some is complain. Okay, the interesting thing is every year people complain that this class is too fast. This year some people say that the class is fast as expected. So I think it's a good sign because ultimately this is the reason why everyone wants S.
The problem counter is we think of the other classes as too slow.
It's not about it.
Yeah.
Okay, so cool. Okay, then after too close, this one is basically a math problem, right? They are only think about it this way. There are actually 13 weeks only, right? Okay? There are 22 missions plus, I don't know, I think 12 or 13 side quests, right? So 30 something, right? So by teacher principle, at least one week must have at least 3, right? Correct. So this time because we have because and then the problem is that it's not so simple because there are weeks whereby there is the midterms, practice exam, those weeks we can't really have assignments due. So essentially the way the assignments are due like this can't be helped. But the point is that the work isn't okay, there's a little bit longer than before based on the side quest. But the missions, the 20 missions used to be 7 problem sets. And we used to have 1 problem set due every 2 weeks. Okay. But on the whole we have found that this new way of breaking up the problem sets into smaller chunks is actually more helpful because it sort of forces discipline on some people who don't have discipline otherwise. Okay. Even now we are seeing some people stacking already. They are basically only doing the problem sets right at the last day. Okay. So this is not a good sign. Okay. The last thing is this: we don't have an A in the class. So officers go like the grades, however. It's very common at this point. I can see some people did well, some people didn't do so well. Those who don't do so well, So the answer to this is hard. I don't really know. But it's expected that I expect more than 70% UKAs. Okay, based on the current. Okay, you all have done better for midterms than the same last year on average. Okay, so I expect more than 70% UKAs. Is it hard? Well, if you look at the ratio, it's not that hard, but my exams aren't the easiest exams on earth, right? And it's possible to blow up. But I suspect it won't really happen. Most people who know what they're doing will be able to do okay. Then some people really will. Okay, for some people it will be really quite hard. Between now and the final exam, I'm not sure how much you can improve. Okay, but we try our best. Okay, now there are other responses. I responded to detail to all this feedback because I think it's important. Because you guys spend the time to give me feedback, then I should spend some time to give you the response. Okay, so more online. Okay, so how do we help people who are a little further behind? Number one, we have buddy schemes. Some of you have given emails. Okay, so hopefully by today, I'll be sending out this email to do the matchmaking. Okay, hopefully the whole point now is that we try to match the students who are killing it to students who are being killed by the class. Hopefully they will help each other. Okay, and this has worked now. Okay, this doesn't work for everybody traditionally, but it works for about 70% of the students. Okay, and this one scheme. Obviously, nothing to do is that those of you who have trouble, whatever, please go and look at the past exams and then go for office hours. Okay, the tutors are office hours Thursday and Friday. But this week, office hours are resumed. Okay, no DG. DG is only for collecting scripts and asking questions on exam. But office hours resumed. Okay, another thing is that we'll read midterm next Tuesday evening. Okay, basically, those of you, this is like a repaper. Second class for those people who didn't do so well. The result for this exam is capped at 60. It means that it's a 100-point paper. Okay, that means you just do it like a normal exam paper. Except for fairness, okay, you will even if you get higher than 60 for this exam, you will be capped at 60. Okay, now who can do this exam? Okay, we don't want the whole entire class to take the exam for fun. Not you who do practice. No, please. Okay, so only the students who have 65 or below can opt to sit for exam. There will not be enough scripts for the whole class. Let me say, you don't compare to straight times, there's enough scripts. I just tell you already. Okay? The room is big enough, but we will only print enough scripts for the students who are below 65. The rest of you fellas, you want to do it fine, it's okay, but we upload the thing, you have to do yourself for time target. Okay? Now, this one will be, obviously you won't get an exam paper earlier than the rest, right? You will get it after the thing's done. So those of you who have below 65, or you are welcome to come back to resit the paper. Okay? Basically, the tutors will be organizing this thing, so it's next Tuesday. Okay? The exams obviously will be the same, probably the same content as the midterm. Okay? The whole point here, okay, so another thing I tell you is that there's some similarity between this exam and the midterm exam. Fundamentally, because you look at where people blew up, and then the question will be set to basically check whether or not after blowing up, you figure out how to deal with this question. Okay, and so this is kind of like redemption for the people who didn't do so well. They don't do above 65, they're fine already. I'm not too concerned. Okay, questions? Alright, so no straight time for not enough exam script, confirm. Yes. Because you score 100. Can it's good. Then I'm a good teacher, it's a good idea. But if you score 100, your point is set at 60.
Is it expected that you score very high?
Typically no. Because the truth is, miracles don't happen. Sadly, I would like to think I'm not a great teacher, but sadly, midterm was last Wednesday, this is next Tuesday, in 2 weeks. Okay, in 2 weeks, if you go from like below 60 to 100, then something was wrong last week, confirmed. Typically, the exams are not so random. I mean, the fact the exams do reflect quite accurately how much you know and what you don't know. Sometimes it's going up because of exam pressure, but the blowout is not 40 points. Okay, it's not quite possible for a student who gets 100 to go to 60. Not like this. So the probability here is so some a few fellas will get okay. My experience, one or two fellas will get 80 something on the exam. Then they're like but then what happened, the score is kept at 60, and these people will almost always get A's in the final exam, in the overall. So, again, this is based on past experience. There will be some students who get A's on the exam. Okay, some students will not get 160 still. But this is like that one. Okay, and then the people who get 180 something on the exams, okay, and what are the people actually? It's very funny that the fellow just blew out. One of the tutors, I can't tell you who, but he blew out completely on the written exam. He had to do the exam last year. He got something on the written exam. And then after he got about 90 something, 80 something or 90 on the final exam. So that's the kind of tutor lah. But the point is that even that your tutor can blow out on the written exam. So hopefully this is consolation for you. Okay? So it happens that because I said it's the first exam, okay, for many of you are at US, and the first kind of exam that tests you not on memorization but how your brain actually functions. It's kind of cool, right? Alright.
For those of us who do at home, can we get someone to pass our code after we do?
Uncle, you have to take something like that, you can pass your code, right? Correct. And what's going to do? Okay, the solution anyway. So you're going to figure out how. Then tell you also basically, if I'm not the thing wrongly, especially because you challenge me in my mental parsing. You all really got some code that is really nasty. Who wrote the most nasty code I read? So you write, you wrote the nastiest code I read in my life. Okay? Like I always popped out, I believe it's code. Okay, correct, frankly. I mean, okay. So, the sad thing about having exams that have very many answers is that it's actually true. Oh my God. Okay? So let's take an exam as a means to the shadow mathematics exercise. Pay for you, pay for me. So very fair. Alright, so let's recap now. So any final questions or midterm or the same stuff is half over. Good for you, good for me. Any questions? Okay, not so hopefully morale is okay. Next week we have you fix out the grades. And then all the people who are having trouble, we know you by name already. Students are already setting up studies for you. This class is very friendly, super hardworking people. Any questions? Okay, thank you very much. Alright, so let's recap. Okay, last week we introduced set is assignment operator. Okay, and today we'll tell you something first. Now before I even start, let me tell you this. Alright, only about 30% of people will understand what I'm saying today after my lecture. Okay? About 50% of them will be blurred. Okay? And 10% have no clue at all. Okay? I do this for you. Okay? This thing that I'm talking about today will not be tested in exams at all. Okay? Because we're talking about the memory model, how scheme actually works. But that's one thing you can see. So I'm just happy. I feel not tested, very happy. Okay? Now the thing is like what we do is to fix this is the following. Okay, next presentation essentially we'll go through the stuff we talk about today in great detail. Okay? So if you give pay attention because it's going to be a bit blur. Okay? But if you're not completely on top of the field, don't worry. Next week we will draw these diagrams until we want to drop it and die. Okay? So just real quickly. So today we need to talk about this thing about how to cope with this new environment. Okay, set. Okay, set is actually a assignment operator. Okay, it's like define. Okay, and today we will talk about why set and define are different. Okay, so set essentially sets a name, a variable to a value. Okay, now so today is this thing called the environment model, which will take up most of the time, not most of the time, half the time, and then the rest will be just mutated data. Okay, now so recap. With this thing called assignments, right, or mutation, the answer doesn't work anymore because why? Your variables are no longer just names or indices. They're actually containers, right, for values. Okay, and because that can change. Okay, so how do you deal with this? And essentially, the first thing to understand is that there's this thing called an environment. Okay, which really is a context in which the expression is evaluated. Okay. And every expression has an environment in which it's evaluated. Okay, this is a kind of definition. At a high level, there's this thing called the global environment. Okay, what does it look like? Okay, so the way to look at the environment is that you can think of it as a frame. So it's like a little box. Okay, in the box you have bindings. Bindings are mappings between symbols and stuff, right? Okay, and at the highest level, okay, when you basically turn on your Docker record, there is already the default environment called the global environment. Okay, and in there there's all bindings, all the default, all those operators that are predefined, all among there. So plus, star, const, list, all this is all there. Okay, already. Okay, so an environment is a sequence of frames. So this is a this is a frame, okay, this box. Now environment is equal to frames, okay, and each frame consists of bindings between from the symbols to the values, okay. Now an environment also, okay, a frame also points to what is called the enclosing environment. I'll show you a bit more later. It's all definitions. Okay, and the way you evaluate a symbol is that you basically look for the value, okay, bound to the symbol within the current environment or current frame. Okay, you can't find a current frame, you keep going up, okay, to find it in the enclosing environment. Let me just show you an example, okay. So the question is this, so this is an example of some frames, okay, representing the different environments. So the question now is, how many environments are there? 2, 3. Answer is 3, okay. So it turns out that A, okay, B, C, and D, they are all environments. Okay, C and D are the same because actually the environment is like this thing. So this is one environment. This thing is another environment. Environment is essentially a context in which you are evaluating a expression. Okay. So basically, if you look at this, the value of x in environment A is what? 7. Okay. Because what happens is that you are in environment A, you check whether or not the current frame has got x bound. If x is bound there, then good for you. It's x is whatever. If it's not bound, you move up. Okay, up the chain until you find it. Okay, so this is 7. X, the x is D really. Okay. Now, so the thing to understand is this. Now, this is where remember your question 4D, right? Basically, you have this thing called shadowing. Essentially, basically there's some variables that have been overwritten by another one. You can't see anymore. So this is what happens. So in frame 1 and frame 2. So frame 2, the x in frame 2 shadows the x in frame 1. So once you're in environment A, you can no longer see the x in frame 1. Okay? What's the value of W in environment A? What's the value of W in environment A? This is called unbound variable error. So what happens is that the interpreter will look at the first frame, cannot find it, go to the next frame, cannot find it. It's not true there's only 2 levels you can meet. Well, in theory, infinite levels. You keep climbing up the whole hierarchy until you reach something called the global environment. You can't find that, sorry, it's the error. Right? Alright, so it's unbound. Okay, so the first thing first, the first thing is this. To evaluate symbol, you just look up, okay? Now, the next thing is important, obviously, is to understand how do you evaluate a combination. Okay, what's combination? Combination is something trying to see if stuff, right? So, obviously, you do this thing called eval and apply. Okay, so just the rule. Now, I will read to you just to tell you what it is, but you probably can't understand it anyway, but you explain to you in an example. So first of all, to evaluate this, so you have combination, okay, then you call it stuff, right? What you do is you eval and then you apply. Okay, now the first thing is that you eval the set expressions of the combination in the current environment. Okay, now by default, if you just open the Dr. Racket fresh, you got something there. What is current environment? The global environment. Okay, simple. Later, so first of all, to evaluate a combination, you evaluate the expression in the current environment. Okay. Now, next thing you do is that you apply the value of the operator, which is likely some kind of procedure, okay, to the sub-expressions of the evaluation. This one is like normal, okay. Now, the funny thing that happens is actually, okay, let me just quickly explain this. Now, so the first question box, which is defined and set, right? Now, what define does is define binds name to the expression in the current frame. In the current frame, okay? Set is different than set rank. Set rank would change the value of the variable in the first instance of that you find as you go up the frame. Okay, so remember I asked you the difference, and you can't explain this last time because you don't know this thing, right? So think about this. There's this kind of frames, right? Now, if you are in the lowest frame, you do a define x3. X3 appears where? Appears here. You do set rank X3. What happens is that the indicator will follow the chain, and the first time it is X, you will set it to 3. Okay, so define basically has locality in terms of setting the thing. Set will actually climb up the chain to set the other value of set. Okay, you'll see that in a while, so this is the key difference. Now, example. Okay, unit W50 in A. What happens? W50 will appear in A, right? A is actually the combination of frame 2 and frame 1. Now, if you do that then X plus X10 in B, what happens? Well, the first thing you do is you do plus X10, right? Which is to look at X, right? So on the right side, you get X can be 7 or 3, but on the right side, X becomes 3, right? Alright? Then you set X to be 13, correct? So what happens is that this thing will change to 13. Very simple idea. Okay, so this is set back and define. Okay, lambda. Okay, lambda what do you do? Lambda, okay, create a 3D object. Okay, which you represent as double bubble. I showed you before, the 2 circles. Okay, and okay, double bubble. Okay, what is double bubble? Double bubble is actually like a coin pair. It's actually 2 pointers. Okay, the first pointer points to the environment in which, so the left pointer points to the code, okay, and the left pointer points to the environment in which the lambda expression is evaluated, okay, and this is known as the enclosed environment. Okay, again, this sounds kind of obscure and not very clear, but we'll see some examples in a short while. Okay, so the key thing that to keep in mind here is that these procedures actually remember the environment in which they are created in. Okay, so this is important because lambda can actually store state, and this is how it's done. Okay, now this is where life is really dicey. Okay, when a procedure is applied, okay, so the two parts, eval and apply. Eval is easy, right? Eval I've gone through, and it is actually not very different from what you expect. Apply is kind of weird. Okay, apply is actually what? Means that you have a operator, some kind of procedure, you have some values you apply, right? Okay. Now, first of all, you create a new frame. Okay, this is where the frame, okay, you have a lot of frames, right? How do they appear? They appear because of the evaluation of the application of lambda. Okay, so when you apply a procedure, first thing is that you create a new frame that points to the environment of the procedure. Remember, a procedure has got two double bubbles, right? One points to the environment, one points to code. Okay, when you actually apply a procedure, you must create a new frame going to the enclosed environment. Okay, and in this new environment, you bind all the form parameters. Okay, this new frame, and then you basically evaluate the body of the procedure in the frame. Okay, sounds very simple. It's very complicated, and especially next week you will see it's very complicated. Can be very complicated. So let's take a look at this. So, simple example, you define square lambda x times x, okay, and this happens in the global environment, right? Now, how do you look at this problem? The first thing you look at is obviously this part first, right? Because you need to eval the expression, and then you bind to the symbol. So when you eval lambda x star x, okay, you generate this double bubble, okay, with one pointer pointing to the enclosing frame, okay, and the other pointer pointing to the code. The code is actually the parameters. Has two parts. The code has two parts: the parameters and the body. Okay. So after this thing is generated, then this is returned as a value. Then you evaluate define. Okay. Define happening in this global environment means that you create a new symbol binding, and you bind it to the value. Right. So this is how you got this thing. Question? So far, okay, yes?
Okay, so if you put a variable inside the lambda that, okay, not the argument, as in the code of the lambda. That
the code there, right?
Yeah, you put something that has not been passed in as an argument, where does it point from?
It doesn't point anywhere, right? This whole thing is just code. All this stuff inside here. So a lambda, okay, so you know that you can put rubbish around lambda and run is okay, right? That means, okay, the point is, the thing to understand, when you do lambda times something, right? you are just creating the double. Essentially, you're just creating a point. Essentially, what are you doing? You are just creating a pair of pointers. Okay? One pointer points to the current environment, the evaluated lambda. The other pair points to some pieces of code somewhere floating in the heap that doesn't not being run yet. So you can put lambda x rubbish and it's actually okay. You only get problems when you try to apply the rubbish onto something. Okay? So at this point, nothing's happening. At this point, you're just creating the procedure. You've not done any application. And obviously your scheme doesn't really any compilation check and everything. So you will have runtime errors if you screw up. But at this point nothing happens. Okay, so basically if you the question here is, let's say again, if you have some extra unbound variable here, what happens? Well, this thing just sits here as code. Nothing happens. Okay? Alright, so let's take a look. Let's go next step. Obviously this is not good enough. I did at some point use this, right? So what happens? Now you're going to evaluate square 5. Okay? So square 5 is what? Square 5 is a combination. So you do what? You eval square, eval 5, and then you apply square onto 5, right? Eval square, you get what? You see, eval square, basically you do a lookup, right, on for the symbol square. What you get back is this double bubble. Okay, eval 5, you get 5. Okay. Now, after you eval everything, you need to apply, right? So what does apply do? Apply must create a new environment, a new frame that points to where? Points to where this enclosing environment is, and you do this. So after that, okay, inside new frame, okay, what you do, you bind the form parameters to the input. Okay, and after that, you write the body of the lambda inside that new frame. Okay, now this is all very simple so far. Okay, the gross things you will see next week in recitation. So after double recitation, after that next week recitation, and you have to draw this at your own leisure, very fun. Okay, you have like a whole chain of frames, like 6, 7, I don't know, 4, 5, 6, 7 frames deep. You understand why this is a mess. Right now it's just a simple example. Okay. Right, so in this frame E1, okay, essentially x is down to 5, and evaluate star xx inside that frame. Question? No, right? Alright.
How is this new frame set in the hierarchy of the existing frame?
I'm not sure I understand the question. Say it again.
What kind of hierarchy will this new frame that was just created be compared to the rest of the frame you had earlier on?
No, right now I only have 2 frames, a global environment and then this one, so there's no other frames. Yeah, of course, this frame will not change. Yeah. So this, once the frame is created, it's there. Okay, when the frame is not there anymore, it will be garbage collected. So you can't be changing this frame. No. You can't be manipulating the frames. No. At least I don't know how to do it. It may be possible, but I don't know how it's done. Okay, so for now, just know that the frame is created. Things happen. After all the operations are done, no more necessary to be garbage collected. Okay. Now, so let's quickly look at an example. Last lecture we looked at this example, which is the big withdrawal, right? So we've shown from last example, the last lecture, that this thing doesn't work with the RSM because it all blows up. So let's take a look at how this works in this new model. Okay, so your W1 make withdrawal 100. Okay, and this is how it works out, right? Now let's take a look. So obviously, after you do make withdrawal balance, okay, this is what you get. Okay, now this doesn't do anything. Make withdrawal balance lambda amount. All it does is it creates a lambda called what? Make withdrawal. Okay, there are 2 lambdas here. There's 1 lambda here and 1 lambda here, right? This is actually what? Define make withdrawal lambda balance. Correct? So you have a lambda balance, and this body, this lambda amount is the body, right? So this whole thing is in the body. Okay, nothing's happening now. All you do in the first instance is you create the lambda, okay, pointing to the global environment because that's where it is actually defined. Okay, all the body gets stuck to the body as code floating somewhere, and then you bind the big withdrawal to this particular lambda. Okay, simple. Okay, this is so quite simple. Now, after what we did is that we did define W1 to be big withdrawal 100, right? Okay. Now what happens is, so the first thing is make withdrawal 100. Make withdrawal, that's what? no withdrawal returns you this lambda, right? 100 returns 100. Then no withdrawal 100 is actually applying the lambda onto 100. So what happens? You create a new frame pointing to the frame that is pointed to by the enclosing frame of this procedure. And then essentially you bind balance inside you bind the parameter inside, and then you bind it to the input. Correct? And then what you do? You go and what? Invert the body of the lambda inside the new frame, correct? Okay? Now, what's the body of this lambda? It's lambda, right? Okay, so what do we do? Okay, this is the body. That means you must evaluate this thing inside here. As you know, evaluate lambda doesn't do much, right? All it does is it creates for you a lambda. It creates for you this object. Okay, pointing to this enclosing the environment in which you evaluated. Okay, and this is the value of that thing. So that means make withdraw 100 to return you this object. Correct? Okay? Now, then there's define W1. Okay? Where is W1? So W1 is actually in the global environment, not in the balance environment. I mean, not in this one. Okay? So essentially, after you do this thing, what happens is you have this kind of a structure, right? You create a new frame, put in balance 100 with new lambda here, and then there's a pointer that points from W1 to this new lambda. Okay? Okay? Okay, so this is how, okay? Now, after you start withdrawing money, right? Okay? So when you do W150, what happens? Okay? You will have to create a new frame, okay? That points to where? Points to this. W1 is now this thing, correct? So to evaluate W150, you need to create a new frame pointing to the frame that is the enclosing environment for this lambda. And then if this lambda has only one parameter amount, okay, you bind 50 to the amount. Okay? And this is actually the code to then run inside that new frame. Okay? This code does what? It balance created an amount. Okay, where is the amount? Amount is 50, right? What is balance? Balance will be found here. So you go up to next frame, you have 100. Then once you have 50 and 100, you can compute minus balance 100. Okay? You then get set balance to be 50, right? Okay? So change the set balance here and change to 50. Okay? And then you return you what? You are here, remember? You're still here. So after that you will return balance. You can't find balance here, you find balance here, and you return 50. Okay? So after evaluating the W150, you get this thing. Okay, now, if you then evaluate W2, make it drop 100, what happens? You will do the same thing, and now you will have a separate frame containing balance 100. Okay? Where you have W2 pointing to that lambda and pointing to this thing. So this is how the lambda is actually creating state. This does not make sense because the two-bank account, obviously there is some separate state. The question here is how is the state being kept? Okay, and this is the picture that shows you how the state is actually being kept. Are we following me? Yeah, very good. Okay. Alright. Now, so pretty much, okay, I have given you the rules and shown you how this thing sort of works. Okay. Now, how do you completely understand what I'm saying? Okay. How many questions? Anybody have any questions before I continue? Okay. It turns out again, maybe I think better this year. Yeah, you're left here, and James ought to be awake. Correct? Right. So the thing is this: all these things sound pretty simple until you get the recitation for next week. Okay, which will appear in IVRE by end of the day. Right. Over there, the examples will reach like six frames deep. Okay, and then it gets really hairy. How these things are being drawn. Okay, but the good news about this whole thing is, first of all, it's not going to be tested on the exam. Because truthfully, this is very skill specific. Because usually it's like not everybody does it this way, right? So skip is this way. Hardly matters that you all know that it's done this way. But knowing this helps you understand how step dying works. Okay? It is not impossible that I use some nasty thing in an exam or something that after you give this piece of code what happens. Okay? And if I give it enough, the thing will be very convoluted. How convoluted? It's just like the pointer, what's the diagram, right? If you draw a diagram out, then you know exactly how it works down. Right? And it's not very hard, it's just very simple. It's just following the steps and drawing out nicely. Okay? Number one. Number two is that next week we will actually go through this in gross detail in recitation. Okay? So what is likely to happen is this, hopefully I will do this. You will get a recitation like today. Hopefully it's not to do, and next week you go and try to draw yourself. Now, if you try to draw yourself and you get stuck, okay, you will have much better understanding next week when I draw it for you. Okay, we'll go together. The problem, however, is that I can make it seem effortless. Okay, when you read yourself, it's not so effortless. Okay? Quite clear, right? Okay, very good. So, now that you are kind of tired, we will watch a little short clip. Okay, it's kind of cute little clip. Have you seen it before? No, okay. right? That's the cute. Now back to business. Alright, so what we've done, and I think you've seen some of this on the midterm exam. Okay, so what we'll do now is we'll talk about mutation. Okay, so mutation really means that you will be able to change data. Right? So far we are doing programming mostly in functional style, which means that you put in stuff things are not mutable. Okay, now we want to deal with mutable data. Okay, so example is bank account. Okay, so the non-mutable data types have a few things, constructors, selectors, predicates, and traces, but no mutators. Okay, today we will talk about mutators. Okay, now the point here is that before RS, before the R6 RS is the version of scheme. Now I think R7 something like that. But anyway, in the earlier versions of scheme and ISO scheme, the const pairs were actually mutable. That means you can const pairs, a const pair is really a pair of pointers, right? In the past, you used to move pointers to change pointers, but now currently in your current implementation of scheme that you're using, you can't change that. Okay, but then obviously that cannot be the case. So now we also have a new version of const pairs which are called mconst, which are exactly the same as const except that they are mutable. Okay. And then let's see. So mconst works like const, except that you use mcar to access elements. Okay. But you can do two things with it. You can do set mcar bank and set mcoder bank. Okay. So mcar and mcoder obviously are the two car and coder pointers, and these two commands allow you to change the pointers. Okay. So set mcar bank xy changes the pointer of x to y. Okay, obviously the encoder will have the same effect. Okay, so we saw this on the midterm somewhat, right? Where you're listing, which is a node, right? Which is a doubly linked list node. There's a front point, there's a previous pointer, and there's next pointer. Okay, and just you can change those pointers. Okay, so this is not a new concept. I mean, it's not a hard concept. It's really quite simple. Okay, what is hard is really figuring out how to use these things in a way which works. Okay, for example, suppose you originally have this thing, x and y. Okay, x is the left side, the top, and then the y is the bottom. Now, suppose you do set mcar bank xy. So, obviously these are all we draw the mconst and the const in the same way, use two boxes. Okay, now, obviously this is the main box, right? This is the car pointer, this is the coder pointer. Okay. So you do set mcar bank xy. Essentially, you take this pointer, which points to this thing. You basically erase this pointer and replace it with a pointer that points to y. Okay. Suppose you do set mcoder xy, what happens? Same thing, right? Except that now the second pointer, okay, first pointer remains the same. Second pointer will now be changed to point to the other thing. Okay, that's all. Right. So this is the pointer. Now. It turns out that in order for you to use, okay, so in the earlier version of const, right, you have many commands like append, list, and things like that. Okay, it turns out that to use those, there's also a kind of like a set of corresponding commands. Okay, but the difference here is that there's an m in front. Okay, and to use operators, you need to do this thing called require. Okay, you need to add a line called require scheme m-pair, and then once you do that, you will be able to call all this list append. Okay, there's no difference. The point now is that these things actually will do similar things to what you used to before, except that now this one operates with the mconst instead of const. So you try to apply this thing to const, you have error. You try to apply append to mconst, you have error. Okay, so it's just a matching the data type. Okay, so suppose you do this. Okay, A is now what? It's now a mutable list of 1, 2, 3. B is now a mutable list of 6 and 5. Now you do define C and append AB. What happens? Okay, C obviously becomes this, right? 1, 2, 3, 6, 5, yeah. Okay, now then if you do set mcar bank B 100, what happens? Well, B becomes 5, right? However, if you check C, C has now become 1, 2, 3, 105. Okay, why is this? Okay, that's essentially C composed of 1, 2, 3. Okay, pointing to B. Okay, so initially this is what you get. Okay, initially the A 1, 2, 3. Okay, B is 6 and 5. When you do find C to be what? M pan A and B, you will do. Okay, remember I think you mentioned before. So when you do a pairing, happens that you create a whole chain of cons boxes. Okay, and basically point to the elements in the first list. And then the last thing will point to the second thing, right? Second list. So this happens. So when you repeat B, okay, C changes as well. Right, question?
Let's say you set M car A 100.
Set M car A 100. So
You will change only A but not C, right?
what do you think?
Because you are creating by yourself, you change.
Correct. So now on the other hand, instead of doing set M car B 100, you do set M car A 100. What happens? This thing here becomes 100. Now, as I mentioned before, the append actually will generate some cons boxes, new cons boxes for the first list. Okay, how does append work? Append generates new cons boxes, both append and append. They will generate new cons boxes for the first list. Okay, at the end, essentially it completes the first list. At the end, what happens? You take the last thing, points to the second list. Yes?
Is it correct to say M append and append are like some like the first type of way to separate the two data types? So you separate by name as compared to if you get 3 ways to message passing data.
Chain operations.
Yeah, it's something like that, right? You just change, you fix it by name.
Sort of lah, but then the whole point here is that you will not typically use this thing interchangeably. Okay. Now basically, the truth is this, right? You actually don't need cons at all. M-cons can do everything that you will do with cons, right? Okay. Now, so the reason why you actually want to use the cons or immutable data types instead of immutable data types is because immutable data types gives you some guarantees. Not knowing that the stuff cannot change is very helpful. Right, I just showed you one problem. One problem here is that if you're not careful about who is going to what, right? Somebody may change some list and you're affected, you may not know it. Okay, and the problem with this kind of changes is that it's very hard to analyze statically. It means you look at the code, right? It seems correct, but in this you change, what kind of code changes this thing? That kind of code changes this thing. But when you do mutation here, you may not know that you're actually changing something over here as well. So this is all quite dangerous, right? If you're not careful. So the reason why you add cons and cons is so that you know exactly what things are changing, what things will not change. Okay, but technically you won't be doing the two. They are kind of you must know what the hell you're doing and do the right things. Okay, so you don't typically do this thing.
So if like the first element in A was mutable, like the first element of A was instead of being 1 was like immutable cons itself. Does that mean if we mutated that, then C would also change?
No.
No?
Oh, if you we change right. So this is good question. So suppose this is not 1. This is the mutable cons. Okay. Now when you click C, you will create these 3 cons boxes, but they will point to the same value that A was pointing to. So it means if this is the mutable cons, M cons, it means you have this arrow point to this thing, and then this arrow will point to that thing. So now you fuck around with A, you actually change C. So that's true. So this is why mutation is a little nasty and complicated. Yes.
So that being said, in this diagram, is this the blue color arrow pointing to 1? Is it the same one as the arrow?
Good question. Is the blue color arrow same one or different one? This is not the number. Integers are special, like symbols. There's only one copy in the entire. Yeah. So this is immutable. Okay. Now the thing to understand is this thing is immutable. One is immutable. Okay, it's a number, right? So yeah, it's the same one actually. But it's a little bit nasty to point to the same one. It hardly matters. Okay.
So if you were an object, if you were a string, and then you EQ it, you still
If it's a string, it's not the same. The question is, if this is a string, good question. Suppose this string is one string, not one number. Then obviously this will point to the same one string. EQ will do the same thing, yes. Okay, so the append operation doesn't actually create new elements. It creates new point boxes, point to the same elements that used to point to by the previous list.
But if you change the string from 1 to 2, C will still point to 1.
C will still point to 1, correct? Are you all lost now? You understand what you're asking here? Okay, maybe I'll just set final exam questions for you to make sure you understand. Thank you very much. Alright. See, I'm telling you what the word alright. How cool is that? Okay, now, next. Alright, so suppose we now run, thank you for the questions, very good questions. Now, define A, M is 1, 2, 3, you get this thing, right? Suppose you now go set, this is fun, okay, you set M car bank to be M coded AA. What the world can I do here? So you just see, okay, M coded A is this one, right? M coded is this one, right? I set M coded is this thing, set to A, which is this thing, right? So how? Okay. So essentially, what I've done is done this obscure thing, okay? And last year at this point, somebody asked a question, and this question we take out as a practical exam. Okay. Practical exam last year was very fun. Okay. Practical exam last year, in case you haven't spoken up already, you should listen. But it wasn't fun again, obviously. But last year, this kind of exchanges. The practical exam was that I give you some random add-con structure. You need to figure out for me how many loops are there inside the structure. Okay, very fun, okay? So anyway, so this you can do, you can actually mutate things and create this kind of loops.
If you do Coulomb point, isn't it just the second law that point?
Okay, second law, this is A, right? M Coulomb A is what? This thing, right? Coulomb again will be this thing, right? So now you are setting the M Coulomb of the second Coulomb, which is, this is the Coulomb of the second Coulomb to A. Let's okay. Now, this is A, right? This one talks to A. M Coulomb of the A is this thing, right? M Coulomb is this thing, right? Now, so this thing is M Coulomb A, right? I'm setting the M Coulomb of the M Coulomb A, which is this thing, to A, which is this thing. So you take this thing and point to this thing. But what?
You're actually setting the thing that the second guy is pointing to, right? So what you're doing is you're erasing the...
I erased it now. Okay, the original version of this, right? Original version of now, right? So I'm setting now to become something not now. Okay? Not so simple. Not simple. Okay, anyway, you can go and figure this out. It's definitely correct. Confirm correct. Okay, you go and take a look and check it out. Okay. Okay. So the question, the real question is, what is the lack of A? Okay. So this is for kicks. You can go figure out for yourself what in the world happens here. So obviously bad things can happen. Right. All right. Okay, so the general idea is this, right? You want to do what? Okay, the kind of common sense answer is this, right? You actually want to count how many const boxes, right? But if you do the typical recursion way, you start with base case. If now A returns 0, otherwise +1, well, life is good. Okay? So for kicks, the last practical exam was given a random const structure. How many cycles are there? Okay, this is the hard question. For easier practice, go and I should have added as a question of the day. For easier question, given a const structure, count how many const boxes are there inside. Okay, not const structure, M const structure. Because if the const structure is very easy, const can only be trees. Because you can't do this. M const is nasty because I can take it and then do random stuff with the pointers. Okay? So the question now is given a M const structure, okay, how do you count how many M const boxes are there in that structure? Okay, this is the first part. Now if you can do that, then the next part will be how you count the cycles, which is harder than the first one. Okay, this is last year's hard question for the practical exam. Okay? Next. Okay, so this is kind of a, yes.
Can we do instead of M const, we just do const. We define A as const x A.
Cannot.
No.
Because the way it works in scheme is, I just taught you the environment model, right? How does evaluation work? You must evaluate the second part first, and then the first part, right? So the first part is define A, right? Second part, but then before you define A doesn't exist, right? So you evaluate the second part, you die, right? So you can't really do cons. That's right. So you can't do self-referential structures in cons because of mutation, right? You can't. You have to create the reference to point to itself before you can actually do it, but you can't. Okay, so it's impossible to create like this cyclical structures in cons test. You need to use the mutable cons. Okay. All right. So now let's just look at this again. We've done this before, right? We've done this in class. Okay. In recitation, we define a queue. Remember what's important? You define what? Define the representation and figure out which is front, which is the back, right? Okay. But the queue that we did in class is a little nasty, right? Why? Because it's a little bit what? Troublesome, right? Remember? You can the two camps. Remember, there's the opposition camp and the pro-government camp, right? And the problem here is that either camp, one thing really sucks, right? Either your addition is order n, or your removal is order n. Okay. So the question here is, can you improve, okay, the implementation and actually have order 1 addition and removal? Cannot. Yeah. How? Yeah, so essentially the whole point is this, right? The key insight here is that if you can, okay, the main problem is this: you need to know the head and the tail. Okay, the problem with the implementation that we did in class in recitation was that you either have access to the head or have access to the tail, and in order to get to the other part, you need to go further down the list, which is a waste of time. So the insight here is that suppose you have a quick way of keeping track of both head and tail, life is good, right? Okay, so let's take a look. So recap. Q is a FIFO structure, first in, first out. Okay, so the items are inserted at the rear, okay, and they are removed from the head. Okay, now there are a few the specs for the queues. First of all, there's a main queue, obviously returns you an empty queue. Okay, and the empty queue will check whether the queue is empty. Okay, and front queue essentially will return you the head element. Okay, and if the queue is empty, you give you some error. Okay, insert queue bank. Okay, the bank notation is important. Now, I think I mentioned before, but let me just say again. The bank, the exclamation mark, is a notation in scheme. Okay, as you know, the question mark, right, is notation in scheme that tells you whether the procedure is a predicate, returns true or false. The bank is notation that indicates that when you apply this procedure to something, it will mutate that element. Okay, so insert queue bank procedure, it takes two things, the queue and item. Obviously, it mutates the queue. Okay, so the queue is mutated, right, and returns the modified version. Okay, delete queue will do what? Delete queue will actually remove the first element. Okay. Okay, nice implementation in recitation 5. Okay. So this is how, obviously, you would try to implement the queue, right? So instead of having just one list of n elements, okay, we introduce extra pair, okay, and this pair keeps track of two things: the front of the queue and the rear of the queue. Okay, why can't we do this earlier? Because earlier we have no capacity to mutate things, okay, which is very important, right? So in here, these are all mutable concepts, so you can actually mutate them. Actually, only this thing is immutable. This thing is not immutable. No, it's wrong. This thing is immutable, sorry. All are immutable. You have to do this. Right, so let's take a look. So how will you add an item? So the point is this: you can decide that this is the front pointer, this is the head, this is the tail. To add item, what happens? You need to add the rear, right? So this thing needs to be mutable because why? You need to go and add to the rear. But after you add to the rear, what happens? You need to basically update this pointer to go and move to the rear. So in this sense, every single one of these const pairs needs to be mutable. Okay, in the past we were dealing with consts that are not mutable, so we couldn't do this. Right. Now, how do you remove an item? Okay, so what's the order of growth for this? 1, right? Because always 2 operations. First operation is that you CUDA on this thing, and then you set CUDA bank to this thing, and then you do what? You do set CUDA bank for this thing to the new element. Okay. How do you remove an item? You basically do a car, right? The car gives you the element already, right? And what happens? You go and set the car gives you this thing, the CUDA of the car gives you this thing. All you need to do is to remove this thing, and then you change the pointer to the first element. Again, this will be order 1. Okay, so this is how you can basically improve the implementation of the queue from having one order n to both order 1. Okay, but to do this, you need to have mutable pointers. Okay. Right. So again, what I just described to you can be obviously written out in words. I mean, in code. Right. So this is the code, right? The front pointer is this thing. The rear pointer is this thing, and then you just write this code. Okay. Set front pointer q item is just set car q item. Set rear pointer is just this thing. Okay. Empty q, just check whether the front pointer is null. Make q, you create a new mcons with 2 nulls. Okay. And then the front q is you basically check whether the q is empty. Okay. If it's not empty, you go and car the front pointer. Okay. And then delete q. Essentially, you check. Okay. How do you delete q? Let's quickly check your understanding. Delete q does what? Delete q removes the not the entire queue. Remove the first element of the queue, right? So what do you do? So the queue is what? The queue is when you get a queue, what you're getting is the first const box, right? This const box points to the front of the queue and the rear of the queue. Remember? So the queue, this is the queue. You're actually getting this thing. To remove an element, you must do what? You must CUDA down. You must basically CUDA down this thing and set this pointer. Okay. So the first thing is, but before you do that, first thing you do is what? Check for empty. Okay. If it's empty, you freak out, right? Okay. If it's not empty, set car bank to the CUDA of the car, right? Okay. So essentially, set front pointer, okay, to the CUDA of the front pointer with the car. Okay. Now, then you return the queue. So this kinds of operations typically return you the mutated object. So the idea is that you use the queue, then it returns you the queue. Okay. Yeah, but this one is this whole point is about removing the head, not about returning the head. Okay. There's another procedure to actually get a head. Okay. How do you insert an item? Yeah, the first thing you must do, yes, Samantha. Correct. You delete the queue. It's not deleting the queue. Deleting the queue is deleting the first element of the queue. So what you're doing is that, okay, this is the queue, right? When you do the delete queue, right, you are actually trying to remove the first element. You just throw the first one away and then you just... Okay, good question. So okay, excellent question. So how do you throw the first one away? Okay, so what happens is scheme, okay, so you're right. So Miss Samantha, you're absolutely right. That means the first one didn't get thrown away by you. Okay, what happens is this, now this is the original state of life, right? So after, what you just did was that I took this pointer, and I pointed it to the second one. That's what I did. Now, what happens then is that this first guy, the A, first piece, will become orphan. Okay? Because the whole point now is that the scheme will do some garbage collection, and one of the things it does is reference counting. So the whole point here is that scheme knows, the interpreter will know for each object what points to it. Okay? Now, what happens is that when this thing that's pointing to it switches to something else, and nobody is pointing to this thing, so this guy is like floating alphabet soup, right? I mean, it's floating in soup. Then there's no way, you can possibly ever access this element ever again. So it will be garbage collected. So you are absolutely correct. Sorry, I was a bit sloppy. Thanks for pointing it out. Means I wasn't very clear about this. But the fact is that A didn't really just disappear. What happened was that when you do this, it becomes non-referenceable. Okay, it means you can no longer access it anymore because nobody points to it. So when that happens, it's detected and then it will be garbage collected.
At what point will scheme occur?
I have no idea, and this is where abstraction matters, right? Someone takes care of it and I don't care. Right, but I mean, I'm just being more less sloppy. But the fact is that you're right that I didn't take care of it. I didn't get rid of it. What happened was that we just removed the reference to it. After a while, the system will garbage collect. Excellent question. Anything else? No. Okay. So now, in terms of how do you insert the queue? Insert an item. You must first create the cons blocks, right? You can use let something lah. Okay, so you create a new pair, which contains two things, right? The item, as well as the noun, right? Then you must do what? You must take the correct. You must check that the queue is not empty. Okay, if it's empty, you do what? You will have to change both. Okay, so the empty one is a bit different. The empty queue, because empty queue you need to change what? 2 pointers, right? Okay, which are the front and back pointer. Okay, if it's non-empty, then you do what? You have to change 2 pointers also, but it's not these 2 pointers anymore. You need to figure out the rear pointer must change to point the new thing, and the rear pointer must then change the new thing, right? Okay, so this is the same thing. You set the rear pointer to set coded to this new thing, and you set the rear pointer itself to point to the new con. So this exactly describes in code the picture that I showed earlier. Okay? Ananta, is it okay? This one is quite straightforward, right? Wang Qi, okay? Alright. M cons, you can use M list item. Can lah. Right, I mean, nothing that, okay. Something that annoys you, no end, Why you write things as, not one, no, or few you write, append list X something, no? No, but why are people using append list X something when you can use cons X something? I don't know what's that, but it's really annoying. Safe Okay, anyway, okay, so removing the items is very simple, right? Removing, you just check whether it's empty. If it's not empty, you can just return. Okay?
Using delete queue, if we have, say, 2 elements left, we do delete queue, then both the front and the back will point to the same element, right? After that, if you do it delete again, then the front will point to null, but the back will still point to that element.
Delete queue. No, the question is whether this emphasis is correct, because he's saying that if you have one element left, and they are now both pointing to, both front and back are pointing to the same.
But the back pointer will still be pointing to what should actually be a completely dead element.
The back pointer will be pointing completely element. Perhaps, let me see, does it work or not? Okay, but it's okay because the point here is this: if the front pointer is now, that is now, and then if you need to add a new thing to the now queue, right? You will actually check whether it's now. If it's now, you place both. So actually, it's okay. Okay, good question. Okay, let me just, okay, this is a very subtle point. Let me just quickly highlight the point. I think it's an excellent point to say. Okay, what he noticed is the following. What Palaf noticed is the following. If you have one element in the queue, okay, and you need the element, what we did in this code here is that I set the front pointer to now. The rear pointer I didn't change. So it's pointing to this one element that's floating in the soup. Okay? Is that correct? Or is it not correct? The answer is that it is actually correct, right? Why? Yeah. So the point now is this: if he's pedantic about it, right, you can go and basically check if it's one element, you change both points to now. It looks a bit cleaner, okay? But my point is the code still works here because this code actually fulfills the contract, right? Okay? And frankly, you get rid of the thing now, it's cleaner. You get rid of it later when you have a new element added, it hardly makes a difference. Okay, it's just one extra cons box. But if you're really, worried about, you think memory is really expensive, you want to save that small piece of memory, you can go and basically null it. Okay? But that's an excellent observation, which is that if you do have one last element, you remove the front queue, the front thing to null, it's still floating around somewhere. Actually, it's referenceable, except that you won't do it. Okay? Alright, so the last thing is that you can create this kind of if you want to do the following, you want to decode the first element and then chop the queue. This is something you can do. You can basically let the result to be the front of the thing, delete the queue, and return the result. Okay, so basically sometimes it's convenient to pull out the thing on the queue. Means on one hand you want to run that element, on the other hand you want to remove one element. Okay. Okay, so what are queues for? These for printing. Okay. Okay, one for example of queue. Okay, we have seen count change, right? Okay, earlier on, for which week? Second, third week? Okay, now let's try iterative version. So this is your recursive count change, right? I'll remember, count change is about what? About taking some amount of money and having some denominations and basically figure out how many ways are there of changing the money into these denominations, right? So this is the code. And remember the recursion? Recursion is the following. Recursion is of the form whereby you partition into two sets. One set is that you use at least one of the largest denomination, one which does not use the largest denomination at all. Right? Okay. Now, so this is what you will do if you write out the whole count change, right? Tree. Okay. Now the idea here is this. Now each of these computations essentially are a bunch of nodes in the tree. So the idea now is to use a queue to keep track of the nodes. Okay, so this algorithm, first of all, you make a queue, empty queue, right? And then what you do is that you take the beginning, okay, the problem is really A5, right? This is the problem, correct? So you create a node called A5, you put into the queue. And counter, you create this variable called counter as 0, okay? Now, if the queue is empty, you stop and return counter. This is iterative, right? This is how it works, right? You come some result to accumulator, and if it's empty, you return. Now, if not, what you do is this: you take out one node from the queue. Okay. Now, if that node is A0, that means if there's no amount, you know there's only one way of changing it, right? Which is all zeros. Okay. And then if that's so, you put in 1 into the counter, add 1 to the counter, and you go to 4. Okay, basically you now throw the thing away and see what else is left. Okay, now if A is less than 0 or K equals to 0, these are the base cases, right? Then you can just take the thing and throw away because those things have no way of actually changing. On the other hand, if these two conditions, these three, 1, 2, and 3, these are the base cases, remember? Okay, these 3 base cases. Right. Now, if it's not a base case, what you do? You will take the node and you actually go and create 2 new nodes consisting of A, K minus 1, and A minus denomination K, and take those 2 nodes and put into the queue. Right. Are we clear? Okay, so essentially what I've done here is that I've used a queue to store state. Okay, so this whole thing essentially I've converted into state in a queue. Okay, and the way that I create all this state is basically the same way that I actually do it recursively, except now the state is just popped into the queue. Okay, who has any questions? Are we okay? Yes.
So we're using a queue in that case, and it's kind of like exploring the tree.
Yeah, we are exploring the tree, right? There's no choice, right?
We use a stack and it would be still.
We use the.
A stack instead of a queue and it still explores the tree.
Okay, good point.
So like, you could.
You could, yeah. No, you don't have to care, right? You just have to, basically the whole point is that this is correct as long as you keep track of the nodes. Alright, so this is a way of doing it. And let's quickly see how we will do this. So essentially we can do count change amount. Okay, queue, make a queue. Insert into the queue, make node amount, whatever amount A, 5. Okay, 5 is the number of types. Okay, and then you call cs1101s14. Okay, and we can define a simple data type, a node. We can use a const to create a node, and then you can use card encoder to get the amount and get the coin types. Okay, so this is how the thing will look. Number one, if the queue is empty, return the counter. Alright. Other than that, you create a new node. Okay, the node you create by dequeuing it from the queue. Okay, you can check the node for the amount and the coin. And this code here, okay, amount 0, coin 0, 0 amount, these are actually your base cases in the recursive version. Right? So in one case, the amount is 0, you know it's one way of doing it, then you add 1. If the amount is less than 0 or 0 coins, you know it's not possible, you just throw the node away. Okay? Other than that, then you know the node, this node is going to be one of those split nodes, right? So what you do is you create 2 new nodes, you shove them into the queue. Okay? So essentially, I'm replicating the same computation process, but instead of doing it recursively by having these kinds of different operations, I'm actually storing the state of computation inside the queue. Okay? So, and then basically I call cs1101s, which means that you go up here and it keeps going until the queue is empty. Right? Yes? It's the amount of time roughly the same, or exactly the same. Exactly the same I mean, you're doing the same thing I mean, huh? Yeah, so it's exactly the same. I mean, you're doing exact same computation. Okay, we're not doing anything special here. I'm just showing you that it's possible to convert a recursive kind of process into an iterative process by using the queue to store state. Well, you tell me the order of growth is what? I don't know. What do you think? Order of growth is what? Time or space? Order of growth, time, same or not? Same lah, because it's doing the same thing, right? You're going through every node anyway. Okay, but obviously it depends on how smart your queue is, right? Now, if your queue is the Restation 5 queue, then life is very hard. Okay? Whereas if your queue is optimized queue whereby, you know, it's actually not ON, it's all O1, then life is simple, right? Okay? Yes? Good question. Will you? So what do you think about this? Think about this. Okay, so the question. Okay, so there are two. Okay, now we use a queue for this thing, right? It works. Instead of using a queue, use a stack. A stack basically means what? A queue is FIFO, right? First in, first out. A queue is LIFO, last in, first out, right? Okay, can you use a stack to solve this problem? Answer is yes. Is there a difference? So think about it, okay? Now, so the question is what's the order of growth? Okay, this is for you to think about and to discuss, okay? Now, what's the order of growth here? Okay? And what's the order of growth if you substitute the queue with a stack? Is there a difference or is there no difference at all? Okay? What is the difference? Okay, great. Okay, now let's quickly, okay, I'm running out of time. Okay, you all answer all questions, very good, but I'm running out of time. So let's quickly go through this. So the table is something that you've seen before in your missions, 12 to 15, right? Okay, so you're doing data programming, you need to shove things to the table, this is what it is, okay? Essentially a table is just a lookup thing whereby you have a key and a value, okay, and then you basically figure out what it is. Okay, the key is the pair, the key value pair is known as entry in the table. Okay, so these are the typical kinds of operations. You make a table, empty table. You can check whether the table is empty. Okay, you can basically look up a certain key to get at the value that's associated with the key. Okay, and if it's not found, typically you return false. Okay, this is kind of cool, right? Because for scheme, okay, typically, you know, anything is not false is true. Okay, so sometimes you can use the return value to test whether or not you can find it. Okay, and then insert. Okay, so insert essentially will put in, has two arguments, the key and the value. You insert the value into the table indexed by the key. Okay, now so this is one way of implementing a table, right? Essentially, you can basically have a queue. I mean, have a list. Okay, where each of the cons boxes points to a kind of another cons box. Okay, this cons box has got two pairs, like one so a pair, one which is the key, the other one is the value. And the way you can actually do this is to do what? You can code down the list, okay, to check whether or not the car, okay, matches the key. If it does, returns a coder, right? So this is how you can make this list, right? You can. Okay, the question is this: why do I have this weird list? Okay, this is the weirdness, right? There's this thing called the table and the star table in front. Why do I have this tag? Is it tag? Okay. All right. I say again. The question is the following: I have this weird-looking thing in front. David says it's a tag. Okay. I will leave this as a question to think about. Why is this thing there? Is it because I like this thing there? Okay. Post. Okay. The forum is a little bit quiet now. We do give out experience points. Only a few people are getting it. So I will encourage you to think about this thing and post in the forum. Why is there this table thing? Now, the thing to think about is what happens if there's no table thing. Okay. It means if instead of having this table, you just have now. Okay, so go think about why you need this list of table. Okay, and this is the kind of implementation. Essentially, you check whether or not, okay, the empty table is just this thing. Okay, now, and to check whether the table is empty, you basically check for equality table with this thing. Right, very simple. Now, look up what you do. Look up, you have this thing called MASSOC, method. Okay, which does the following. Okay, MASSOC, what it does is that it will cool it down. It's normal kind of a list processing operation. Cool down the list. Okay, checks for the car. If the same, returns a CUDA. Okay. All right. Sorry, I'm a little bit slow because today a lot of questions. So let me quickly finish up. So insertion of record. What you do is that, how do you insert a record in the table? You first check whether the key associated with the record exists. If it exists, it means the record exists. Okay, then you just go mutate the record. Okay, so you see here, I'm doing a lookup. Okay, this record will be lookup. If this record cannot be found, a record will be false. If it's true, I just mutate the value of the record. If it's not true, then I will do what? I will basically add a new cons, okay, to create a new record. Okay. Now, so how do you, for kicks, go and figure out how to delete this key from the table. Okay, so you can actually implement 2D tables, because sometimes you have 2D and 3D tables. Okay, and what you can do is you can implement it as a nested 1D table. Okay, in fact, I think you do 2D tables for your missions 12 to 15. Okay. Essentially, this is what it looks like, right? You have a table, and then you basically have tables of tables, okay? And essentially, yeah, you just have to do lookups, okay? So essentially, this thing is your first key, okay? And then after that, this other thing will be your second key. It means this table lookups will be like X, Y, okay? The key is not one thing, but two things, okay? So how do you use tables? Well, the tables is for various things. For example, if you want to do a word counting, okay, you have a little song which you all know. Who here doesn't know the song? Who here knows the song? Who here doesn't know the song? Paulina, you know not? Can I take first now? Okay. Okay, so anyway, essentially you can use a table to keep track of how many words there are for each of the words, okay? And then the way to do it is just to cool down the message list, right? And then every time you see a word, right, you do a lookup, okay, find the entry, and then you can go replace the entry if it exists with increment by increasing the counter. If not, you create a new entry with counter 1, okay? And then obviously you can ignore punctuation. Okay, so for cakes, think about whether you can find any other applications that require queues or tables. Okay, and the thing is this: to understand that you know, even infinite data structure, you can always have, in fact, infinitely many representations. Okay, so in fact, it is possible to go and implement a queue with a table. Okay, it's a little odd, but you can do it. Okay, and how do you do this? Okay, essentially an empty queue can be an empty table, right? And to insert an item M, okay, what you can do is that you can actually insert entry NM into the table, okay, where N is a random number, you automatically generate, okay, to actually serve as a unique key in the table, okay. So after you insert an element, you increment N, okay, so that you can keep track of what the head and tail, the last item is. Any reason? Next lecture. You are covering Wei Sang? Teaching. Oh, okay. Alright, so the last thing is this, and indicates the order. Yeah, so after you insert an item, you go increment N, okay? So this is how you can actually do this. So to the item, essentially you need to do a lookup, okay? For S, which is the smallest key, okay? And then you can do the entry and increment S. Okay, essentially what we're doing here is this. Remember, in the queue, right, you're actually keeping track of 2 pointers. The front pointer and the rear pointer. Okay, so the whole point here is that you can actually emulate all this operation using a table. Okay, so the question now is how would you implement front queue, which does what? Which returns you the head of the queue, right? And what is the time complexity of this operation? Okay. So the next question is, can you implement tables using queues? Okay, so this again for you to think about. All right, consider using 2 queues. Okay, think about how to represent an empty table with queues, right? And how to implement table operations. Okay, like lookup, insert using queue operations. Right? Okay, I've got to go already because the next lecture is coming in. Okay, so the question is, can you implement a table more efficiently? Okay, the answer is obviously yes. Okay, now I'm not saying at this point these questions are for fun. Okay, like many questions that we have in class they are not really real questions, right? They are kind of for fun, like really quite ridiculous things that you never actually do, but we do it because you want to understand concepts. Okay, summary. Today what we've done is that we've talked about the variant model. Okay, and this is something that we discuss much more detail in class next week recitation. Okay, and I guess that's just pretty much it. Okay, so today sorry a bit slow because there were many questions, but I think they're very, very good questions. Okay, so thank you very much. Anybody has any issues with the midterm exams, come and see me. Very generous today. Santa Claus, I'll give you more points, no problem. All right, thank you very much. Brian, you need to use this machine now. And you have you need to lock up, inside the